All right, so we'll start out with number 3 from 6.3. So we are looking at a circle here. We have some information presented to us, which is that OV and RS are perpendicular. So we got them meeting at a 90-degree angle there, and that's going to tell us some stuff about how it's going to intersect. We have OV is 9, and we have OT is 6. So let's start by labeling some information. First thing I want to grab is this is a right angle. Whoops. Oh no. Here we go. Let's try. There we go. And then let's do this in orange. So got our 90 here. I'm going to do some stuff in orange here, which is that OV is 9. So I'm going to say this whole distance from here to here is 9. So if O to V is 9, what would we call OV? OV is the radius. So all of my points to the radius are going to be 9. So that means OR is also 9. So I'm going to label it, although that wasn't like directly given to us. And we're also told that OT is 6. And I'm going to try and highlight just, oops, keep on hitting the other button there. There we go. So that OT segment there is 6. So when I'm looking at this, I want to find RS. So RS is going to be the length of this chord here. And since I know this is perpendicular, I'm basically given a right triangle. So the right triangle that I am looking at here has my top point of R. I have this point here as T, and I got this point here as the center of my circle O. So the length that I was given was ST. That's it. I don't know. Yeah, it looks like a right angle enough. So label my right angle there. We got OV, which is the radius. So this is going to be OV as well. So this point out here is going to create RO as 9. I was told that TO is 6, and I don't know what this thing is, so I'm just going to call it a variable. The variable I'm going to call it is Z. We don't use Z enough. So looking at the reason we don't use Z is because it looks like 2. That's why. I don't know. We'll just use X. We always use X. X squared plus 6 squared equals 9 squared. And I do some math, so I get X squared is equal to, now here's 81 minus 36, which gets us 45. And then I get my X value, and it would be plus or minus, but since we have a length here, it can only be positive. So I'm going to simplify this thing to, oops, 3 root 5. So square root, factor out of 3, only keep the positive one. That's the value for X. Since my X value is 3 root 5, and this only represents half of the distance that I want, because I want to go back out to here. And if I'm intersecting perpendicular to a chord, I know that I'm bisecting it. That tells me that RS is going to be 2 times this thing, so it's going to be 6 root 5. Any questions there? Perfect. Good to go. Let's take a peek at the next one. So for 7 here, I am actually going to probably copy this twice because I'm going to want to write on it. So do this. First one we'll do, I already forget the numbers, my old age, 17 and 15. All right, so starting out with 7 here, I am given some information, which is that AE is 6. So I'm going to label this in red, and I'm going to say it's 6. I'm also told that EB, which we'll do in orange here, is 4. I am told that DE, we'll do it in blue, is 8. And I'm trying to find EC. So we'll do EC in indigo here. And I don't know what that thing is, so again, I'm just going to call it X here. So looking at this, there's a relationship between the intersection of 2 chords, which is that if I have this times this, it's going to equal this times that. So when I'm setting this up, I'm going to have it as 6 times 4 is equal to 8 times, oops, I put X there in the wrong color. 8 times X, there we go. So now I just do some math and solve this thing. And X equals 3. Any questions on this one? Perfect. So same relationship is going to hold for 15 here. It's just that we're maybe given the information presented slightly differently. So I think this is slightly more interesting the way it presents it, saying a ratio between these things, because really it's just going to force us to have an X and a like 2X value. So let's look at this one here. So looking at 15, we have AE, which is 9. I have EB, which is 8. Then we've got DE to EC is 2 to 1. So if I had DE and I were relating it to EC, they would be 2 to 1, and I don't know what they are, so I'm going to call it 2x to x. So this is really like the tricky part of this problem, is just getting this concept. So I'm going to say DE is going to be blue, and I'm going to say this is 2x, and then we'll call our x value purple here, and that is EC. So there's x. So now I'm still just going to set this up the same. It's just now that we get to a point where I'll have to set up and solve a quadratic equation. So 9 times 8 is equal to 2x times x. So I get 72 is equal to 2x squared. 36, whoops, equals x squared. And I get my x value of 6. Again, I cannot have my negative value, so I don't need to even bother do the whole plus or minus part here. Any questions on this one? Perfect. All right. Let's see what was next. 21. For all these problems, guys, the best thing I would recommend is just to check out that very last page in the chapter. It's like the light blue sort of summary of all the things. I include it in both the lessons, but like that summary is really going to be, I think, the best thing for problems like this. All right, enough of that. Let's start doing this one. We have RS is 8. I am told that RV is 12. It's the full distance here. And I'd really love to know what RT is. So we'll say that is in blue. And I don't know what that is, so I'm just going to call it X. So if I have a tangent and a secant, the way that I'm going to set this up is my tangent squared is equal to the first intersection and then the second intersection. So I have 64 is equal to 12x, and then I get x is 16/3. Any questions on this one? Perfect, perfect. Let's take a peek at 29, then 31. Cool. So here we have a polygon which is being circumscribed about the circle, or we could say we have a circle inscribed in a polygon. This thing's a quadrilateral, blah, 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 blah. We're trying to prove that AB plus CD is equal to DA plus CB. Let's see what I want to do it then. Do you need to go here? So as we're looking at this one, we've got some points that are tangent here. We're going to want to label all these points. So the first thing I would do is I have point of tangency, point of tangency, point of tangency, point of tangency. So I'm going to label all these things. Let's have, how do I want to label them? Just do like M, N, O, P. We'll go around like that. Actually, I don't want to use O twice. So let's do PQ. So now we're looking at these things. We have these points M, N, P, and Q respectively for DC, DA, AB, and BC. So when we look at these things, tangent segments are all going to be congruent here because that's the radius of my circle. So I'm going to label this with a line out, line out, line out, and a line out there. And then from there, we can say all these segments are congruent. So I don't know, I'll put a little one tick on them, even though we don't really need to. So I got all those things. So now as we look at this thing, we can say basically I've got how do I want to label this? Let's do it in our lighter purple color. Sorry, if I talk while I'm doing this, I'll for sure write the wrong thing down. I'll summarize in a sec after though. Q, CQ. I kind of wrote these out of order over here. I'll do this. I'll do underline, underline, and I'll do one big underline for these ones. Oops. Okay. So, how do I want to start this? So we've got our chunks here that I've got a isosceles triangle essentially being created. So like when I'm saying each of these chunks, did I label all the individual chunks? I have to label those. So there's so much writing here for this. I'm sorry that it takes me so long to write these things out. Maybe I can just write out like, I don't know, I should write them all out. PB, oops, equal to BQ. So if you guys see what's happening here, basically we're going out, we're creating individual segments. So like this red here and this orange here are going to be congruent, and then I'm going to have these two parts congruent, these two parts congruent, and these two parts congruent. So I can say, okay, if this and that are the same, and I'm saying these two chunks like blue and orange added together are the same thing as red and green added together, I'm saying like, here's the little chunk, here's the little chunk. Okay, those are equal. Here's a little chunk, here's a little chunk. Okay, those are equal. Big chunk, okay, big chunk, okay. So that's what I'm going through and writing here. It just takes me 18 years to do it because that's what we're dealing with. MD is equal to, oops, there we go. What DN? Okay, finally. Holy moly. So as we look at these things, if we wanted to do substitution, basically we're able to substitute in for all these. I don't know if it's even worth me going around and doing tick marks for them or doing other colors. So let's just like focus on this. So just focusing on AP and AN, as I look at this thing, this distance here is going to be the same as this distance here. And the reason is if I were to connect these with a line, here I have an isosceles triangle. So I know that this is going to end up creating another isosceles triangle as it comes out here. If you want to use it using an inscribed angle to its intercepted arc, you can do it that way. So again, inscribed angle coming out like this, another set of isosceles sides here. So I know that this side is the same as this side, and then from here, I'm getting that at this vertex, and at this vertex as well. So for each one of these respectively, I'm getting, okay, these segments are the same, these segments are the same, these segments are the same. So if I were to just label this as like segment 1, it's equivalent to this segment 1 over here. And then if I say segment 2, this is segment 2, this is segment 3, this is segment 3, here we got 4, and here we got 4. And now if I look at what would happen if I took A, B, and CD, well, AB just gave me 4 and 3, and CD gave me 1 and 2. So I got over here 1, 2, 3, 4, and if I take DA and BC, I got 1, 2, 3, 4 as well. So that's how we're getting those two are congruent. Does that make sense? People want me to go into more detail than that, or is that good enough? Again, we always have our tangent segments from an external point are congruent. So whether you're doing it that way or whether you're just using your triangle and flipping it from the inscribed angle, both get you the same thing. Cool. How does it follow from exercise 30 that this thing is congruent to this thing? Blast it. We need exercise 30. Whoa. There we go. Alrighty. So looking at this one here, triangle ADE, congruent triangle CBE. What can you conclude about AE and CE? Conclude about DE and EB. We're gonna say they're similar. They're congruent. All right, so these are congruent, and these ones are the same. So that's our conclusion here. I'm just gonna jot that down before I go into like a super long explanation of it. So yes for congruency, and then both congruent as well. So basically the first thing is it's asking, does it follow that ADE is also congruent to CBE? The answer is yes, they're both congruent. What can you conclude about AB and CE? And what can you conclude about DE and EB? Both congruent as well. So here we're starting out basically saying we have AB and DC are the same. So this segment is going to be the same as this segment. And so I've got this, and we have squiggle. We're trying to prove these two triangles are the same. So basically when we're doing this, I personally would use the inscribed angle here and going out to this arc that gets created. And I'll use this angle that gets created here. So like in doing this thing, basically we've got these two arcs that are the same. They're inscribed angles. If I add them up, they're going to be the same. So arc addition postulate, we substitute some stuff in, and we get congruency there. So in a super fast nutshell, that's like how we do problem 30. And now we're assuming we did problem 30. We proved this ABD, so A to B to D is this bigger triangle, and we have CDB, which is this bigger triangle over here. And now we're talking about these smaller triangles. So let me highlight these, ADE. So we got this little green one and this little green one here. So when we're talking about these things, versus these angles, then because they're congruent triangles, they're gonna have corresponding angles are congruent. So I already get an angle there, which is one way of doing it. It's not the only way though. Like we can also just use this an inscribed angle going out to the same intercepted arc. So both of these are going out to the intercepted arc of, DB. So this angle is going to be this angle here. We get this is a vertical angle right in the middle, and so therefore we have our third angle as well here. And then from there, basically, we can look at this thing and say, now that we have two congruent triangles, what else do I want to say about this thing? So we got yes. So if they are two congruent triangles, then their corresponding sides are congruent. So here and here. And then we have, oopsie, wrong one. DE and EB. So that's probably super hard to see, but I don't know. Are there any questions here? I feel like I'm just re-explaining stuff here that hopefully it's fairly clear. Okay, cool. I'm going to take the silence as we're good on this one. If it got a little convoluted, I wouldn't worry too much about it as long as you are good with the conclusion there. End our recording here.